So welcome back students to one more session of your Bahadur chemistry. So we've been doing almost 20 questions till now. So let's start and come back to do the 21st question. So here in this question, let's read what is given to us. So what is the energy in joules required to shift the electron? Okay, so let me remind before I do. In my previous videos, I have done the structure of atom numericals. In that I have completed almost 20, total of 60 numericals are there. I have completed 20 numericals, all the concepts starting from discovery of electron till the last, that is your quantum numbers, are covered in this series. So this is the Bahadur chemistry numerical series. Please follow the earlier videos also. Okay, now let us come back and read the question. So here they've given us what is the energy in joules, okay, required to shift the electron of hydrogen atom from Bohr's first orbit to the fifth Bohr orbit, and what is the wavelength of light emitted when the electron returns to the ground state. So the ground state energy level, electron energy level, is minus 2.18 into 10 raised to the minus 11 ergs. Okay, so basically they've given me, what should I find out? I need to find out energy in joules. Okay, what energy in joules, that is delta E, when the electron in the hydrogen atom is shifting from the first orbit to the fifth orbit, right? And I should also find out the wavelength, isn't it? Right, so both the things I need to find out. So let's start. So first of all, we have a formula in Bohr's hydrogen atom. What is the formula? First of all, let us note what is given. Here they've given me only one value. Let me note that. That is your energy in the ground state, which is equal to 2.18 into 10 raised to the minus 11 ergs. This is the first thing which is given to me, right? I need to find out what, and we also have a formula, isn't it? Earlier we have studied, that is En by En square, isn't it? We have studied in the earlier videos also. So according to that, I'll just go directly with E5. E5 is equal to minus, okay, this is minus 2.18 into 10 raised to the minus 11 divided by, for the fifth orbit, isn't it? So 5 square, that is nothing but 25 ergs, isn't it? Yes. Now I need to find the energy in joules. So what is the formula which is related? The formula is delta E is equal to E5 minus E1. First applying this formula, that is En by En square. So En is equal to E by N square according to this formula, right? So this gives the energy, whichever energy level is given. So after that, we'll be doing this formula E5 minus E1, isn't it? Right. So what is this equal to now? Delta E. So just let us the same thing. Let's solve. Minus 2.18 into 10 raised to the minus 11 divided by 25. By 25. Fine. So plus, right? So minus of minus, this becomes minus of minus. So plus, now what am I writing here? Okay, let me write this number here. So I'm writing the same thing. What is E5 equal to? Minus 2.18 into 10 raised to the minus 11 divided by 25 minus of minus, again the same value, 2.18 into 10 raised to the minus 11. So what does it become to? This comes to basically minus 2.18 into 10 raised to the minus 11 by 25, plus minus into minus is plus, 2.18 into 10 raised to the minus 11. So when I solve, I get an answer of 2.09 into 10 raised to the minus 11 ergs. So this is your energy. Fine, right? So now what did they ask me? The energy, they've asked me to find out lambda also, wavelength also, isn't it? Yes. So what is the formula we have studied for the wavelength? Delta E and wavelength. Delta E is equal to Hc by lambda. We have studied this formula, isn't it? Yes. So let's substitute. Let me turn the page and use it. So Hc by lambda. So Hc by lambda. So I need, okay, let us write the formula. Delta E is equal to Hc by lambda. I need to find this quantity. Send this quantity here, send this quantity. Lambda is equal to Hc by lambda E. So lambda E value we already got. Let us substitute. H is what? Planck's constant. 6.626 into 10 raised to the minus 34. Velocity of light is 3 into 10 raised to the 8 meters per second divided by delta E value. We previously got 2.09 10 raised to the minus 12. When I solve this, I get an answer of 9.51 into 10 raised to the minus 4 centimeter. Okay, the same thing if I have to write it in angstroms. So what is when you convert it into angstroms, this becomes 951. You're shifting the decimal, so 951 into 10 raised to power, okay, 951 angstroms, that's it, isn't it? So now I'm shifting, so this becomes equal to angstroms. This is your sum. Hope the concept is clear. Let's come back into one more numerical. So here in this numerical they've given me, let's read. The electron energy in hydrogen atom is given by, this is a formula which we have already learned in the theory part. Fine, En level. Calculate the energy required to remove an electron. I need to calculate the energy required to remove an electron completely from n is equal to 2 orbit. Okay, and what is the longest wavelength of light in centimeters that can be used to cause this transition? Okay, so they've given the formula. They've also given, they've asked me to find out the energy required. Okay, and what is the longest wavelength. So both the things I need to calculate, energy as well as wavelength. So let us start with the numerical. So first let us note which energy I need to find. Calculate the energy required to remove an electron from n is equal to 2. So substitute this formula first. En is equal to minus 2.18 into 10 raised to the power of 8. So instead of n, so this is n square, that is nothing but minus 2.18 into 10. I need to find the energy for electron when it's this one, when remove the electron from n is equal to 2. So instead of n, this becomes 2 square, isn't it? Yes. So this, when I divide, I get an answer of 5.45 into 10 raised to the power of minus 19 joules. This is over. Now I should also find out the longest wavelength, isn't it? So what is that formula? So let us take this. Now this is what En means. It's nothing but E2, because n is equal to 2. So let me write the formula. Basically we have this formula, E is equal to lambda, but here in this case E is in which form? E2 is equal to Hc by lambda, isn't it? So what is this now? So basically they've given this whole thing. I need to find lambda here, isn't it? So now what actually is this energy value? This is how much? This is nothing but this value, isn't it? 2.18 so 2 square. So this value I can directly to prove this, only this value, energy value is only so much, isn't it? So let me write the formula. From this formula I need to find lambda. Let us substitute. H is how much? 6.625 into 10 raised to the power of minus 34. What is velocity? I need to find lambda. So velocity is 3 into 10 raised to the power of 8. Okay, now what is this value, energy value earlier? It is nothing but 2.18 into 10 raised to the power of minus 18 by 2 square, isn't it? Right, that energy value. So what happens when I cross multiply this one here? This value is, okay, this value is this value, isn't it? So when I cross multiply this, 2 goes above, isn't it? So this becomes your 2 square divided by how much is your this one now, energy 2.18. so 2 square, this value is so much. When I took the reverse, 2 square goes above and this value comes down. That is nothing but 2.18 into 10 raised to the power of minus 18. How much do I get? I get an answer of 3646 into 10 raised to the power of minus 8 meters. Further, if I write in centimeters, this becomes 3646 into 10 raised to the power of minus 6 centimeter. You can also write this as in angstroms. How? 3646 angstroms. So how am I writing directly now? Please see in the first video where I did wave characteristics, I've shown you all the conversions. How to convert into meter, how to convert into centimeter, how to convert into angstroms, all the conversions I've shown it. So please watch that video so that you have a clear idea how am I converting. So I have got 3 answers. One is in meter, one is in centimeter, one is in angstroms. So basically the same formulas I'm applying again and again. Let's come back and do one more numerical. Now this one, what is this numerical asking us to do? Let's see. So here, according to Bohr's theory, the electronic energy of hydrogen atom in nanometer, hydrogen atom in nth Bohr orbit. Okay, Bohr's theory, the electronic energy of hydrogen atom in nth Bohr orbit is given. The same formula is given. Okay, now what should I do? I need to calculate the longest wavelength that will be needed to remove an electron from third Bohr orbit of helium plus ion. Okay, very interesting thing, isn't it? Right. So third hydrogen ion. Okay, let's do the sum in this way. So basically, when I have to solve, what should I find out? I need to find out, they said E3, this is important. Calculate the longest wavelength of light that will be needed to remove an electron from third Bohr's orbit of helium plus ion. Okay, this is what they have given. Fine. So let's write. So according to this formula, now En is what one for the hydrogen. First of all, En is nothing but I am comparing between the longest wavelength that remove an electron third Bohr orbit of helium. I need to compare. So I am instead of that, see here this is electronic according to hydrogen. This is the formula, but I need to compare with helium. So what formula will I write? E3H is equal to minus 21.76 into 10 raised power of minus 19 by what is N? 3, isn't it? So 3 square. When I solve this, I get an answer of 2.41 into 10 raised power of minus 19 joule. Okay, this is the thing. Fine. So now what did they give me? They said I need to compare E3 of helium, third Bohr's orbit of helium, okay, which is equal to Z square into E3 of hydrogen. This is important. Okay, this is a formula actually, but what we did is we are comparing, because the question demands comparing between helium and hydrogen. What is this? Now here your Z is nothing but atomic number. Helium, hydrogen, helium. Helium is 2, 2 square is 4. So let's substitute. Fine. So let us write now basically what is E of hydrogen, how much you take it? Z square is how much? 4 into what is E of this one? It is nothing but minus 2.46 into 10 raised power of minus 19. So when I solve this, I get an answer of minus 9.64 into 10 raised power of minus 19 joules. Okay, this is over. Fine. I have compared both. Now, so what did they say? Now, if I have to remove the electron from third Bohr's orbit, so orbit energy equivalent to almost 9.64 into 10 raised power of minus 19 should be provided. If so much energy is provided, then only I can remove an electron from third Bohr's orbit of this helium. For helium, so much energy I have to supply. Then I can easily take out the electron. Fine. So now what else did they ask me? The first part is over. Next part is calculate the longest wavelength of light that is to be needed to remove an electron. Okay, longest wavelength also I need to find. So what is that? Basically, I know earlier formula E is equal to hc by lambda. But what is now? This is third orbit. So this becomes E3 hc by lambda. I'm taking lambda above, I'm taking E3 out. So lambda is equal to hc by E3. Okay. Now what is H? Planck's constant 625 into 10 raised power of minus 34. What is velocity of light? 3 into 10 raised power of 8. 3 raised power of 8, not minus 8, 8. Now E3 value, how much did I get earlier? I got almost 9.64. Okay, let us write that. It is 9.64 into 10 raised power of minus 19. When I solve this, I get an answer of 2.061 into 10 raised power of minus 7 meters. Okay, done. Now I can also write the same further. Lambda is equal to, now when I shift this decimal here in this direction, 2061 into 10 raised power of minus 10 meters. Now further write it in angstroms. Yes, so I can write it in angstroms, isn't it? Because 1 angstrom is equal to 10 raised power of minus 10 meters. This is 1 angstrom. So instead of this value, I can write it as 2061 angstroms. This is done, isn't it? This is your sum. So simple. Try to compare with hydrogen. Equalize this according to the formula. Get the answer and substitute in this. Let's come back and do one more form, numerical. Now, what do they give me here? In this numerical, calculate the wavelength and energy of radiation emitted. Again, the same concepts. They're moving around only 2 formulas. So, once I do so many numericals, it will be easy for you. You also keep practicing like that. Calculate the wavelength and energy of radiation emitted for the electronic transition from infinity to stationary state for one hydrogen atom. Okay. What did they ask me? They've asked me to find out, yes, wavelength and energy of radiation. Okay. So when the energy of radiation emitted for the electronic transition from infinity, E infinity to stationary state. Okay. E infinity to E1 for hydrogen atom. Simple, isn't it? There's nothing. Let's write. So what did they give me here? They've given state. There are two things. One is infinity and one is stationary state. So one value n1 is given as 1. This is your stationary state. N2 value is given as infinity. Both the values. Okay. Now, according to this formula, I need to find the energy, isn't it? We have a formula, delta E is equal to E infinity minus E1, because from that only, transition is happening from infinity to stationary state, from infinity to stationary state. So E infinity minus E1. So what is E infinity? E infinity is always 0, isn't it? Minus of, how much is E1 value given to us? Here it's given minus 13.6. When I subtract, I get an answer of 13.6 electron volt. That's also over. So now, but here this is for electronic transition, isn't it? So to get your this one in joules, what do? We multiply with the charge, isn't it? So this becomes equal to 13.6 into 1.602 into 10 raised power of minus 19 joules. When I multiply, I get an answer of 217.9 into 10 raised power of minus 20 joules. Fine. So this is your electronic transition energy. Now I need to find wavelength. This is part A. This is part B. Because they've asked for the electron, so I've taken the charge of electron. Now I'll find out lambda. So what is the formula which we know? Delta E is equal to hc by lambda. I've been writing the same formula again and again. Our lambda is here. Take this lambda here, get this E here. What do I get? Lambda is equal to hc by delta E. Delta E value is already here. Now write down. Planck's constant value is into my 10 raised power of minus 34. Velocity of light is 3 into 10 raised power of 8. Delta E value which I got is 217.9 into 10 raised power of minus 20. So lambda, how much do I get when I solve? I get an answer of 9.12 into 10 raised power of minus 2 meters. That's fine. So further, you can also simplify this by writing. You can shift the decimal. You can write it as 912 into 10 raised to the power of minus 10 meters. Okay, this is 10 raised to the power of 8, no, not 2, 8. Okay, 8, I'm sorry, 8. So you shift this, you get 10 raised to the power of minus 10. Further, you can, this is one answer. How can you write further this one? You can also write it in angstroms as, because 1 angstrom is 10 raised to the power of minus 10. So this becomes 912 into 10 raised, 912 angstroms. This is the answer. So this is in meters, further simplified, and then we have written one more meters, further simplified. I have written in angstroms also, right? Hope the concept is clear, right? So we've been doing energy, wavelength, numericals only, so that the concept is clear. Now let's come back and do one more numerical Bahadu chemistry. Here, what did they give us? What transition in the hydrogen spectrum would you have the same wavelength as Balmer transition n is equal to 4 to n is equal to 2 of helium spectrum? Okay, so they've asked me what transition of hydrogen spectrum would you have the same wavelength as the Balmer transition, it seems. Okay, fine. So I need to find the transition, which transition is similar. For that, what is that? First of all, which one should I compare? What transition in hydrogen spectrum would have the same wavelength as Balmer transition of helium spectrum? So I need to start with helium. I am comparing that one with this one. So start writing. So for helium, okay, what is the formula? 1 by lambda is equal to Rydberg's constant into z square by 1 by n1 square minus 1 by n2 square. This is the formula which we have learned. Now what is Z? This is for helium. Okay, let us write the atomic number of helium. 1 by lambda is equal to RH into 2 square. Helium atomic number is 2. So 2 square is becomes 4 divided by, from where n1 is what, right? So basic thing, what this is the basic one is 2, isn't it? This one 2, the ground state. So 2 square minus, it is 4 square. This is for your helium atom. Now let's come back for hydrogen atom. Hydrogen atom, this is for helium and this is for hydrogen atom. Here they've given helium plus, so I've taken that. Here this is for hydrogen. Now the same formula implies here 1 by lambda is equal to RH into what is the atomic number of this one for hydrogen. Basically, like normally if I have to write here, atomic number is 1 square only, so nothing to write in this case. So I'll be writing as 1 by n1 square by 1 by n2 square. Okay, I have hydrogen and this one. Now let me name